Let's consider the problem 1325F, Ehab's last theorem. In this problem, we're given a graph with n nodes, m edges, n is up to 10 to the power 5, and we have to find either an independent set that has exactly ceiling of square root of n vertices, or a simple cycle of at least square root of n, ceiling of square root of n vertices. And I'm just going to refer to ceiling of square root of n as square root of n from now on, because it's easier to say and has pretty much the same meaning. Okay, let's first prove this thing that they said, that one of the two is guaranteed to exist. So let's consider we have a graph, right? Either there is a simple cycle of square root of n vertices, or there is not. So if there is, we've proven that there is one of the two, right? Or there's an independent set. So if there's a simple cycle, we've proven that one of the two exists. If there's no simple cycle, well, we can show that each node is it's either part of a simple cycle or it's not, right? So there's no simple cycle of size greater than square root of n. So what this means is that if every node is inside a simple cycle, then we can simply take one node from each simple cycle to get a square root of n vertices. Like in this example here, we can just simply do that. Okay, however, it's not always the case that every node is inside a simple cycle, right? You may have something like more of a tree-shaped thing, where, like this, where there may even be a cycle part of it with an extra node hanging off. But let's just consider more of a tree-shaped thing for now. Okay, what do you do with a tree-shaped thing? Well, let's just say it's connected to a cycle here, and you have, so we can make all the cycles one big nodes, right? So there could be another cycle here. Okay, with a tree-shaped thing, what we'll do is it's very simple. We'll take all the leaves. And when I say that we're taking this cycle here, I basically mean we're taking one node in that cycle. It doesn't matter which node. And then we'll go up the tree, we'll take whatever we can. So, because we took this node here, we cannot take this node, that's off limits, so we will take this node here. And then we will take one node in here. And it doesn't matter if it's a little off. Let's just say instead of, so we have something like this, then we could take this node, and we still cannot take that node. Load for a second. Yeah, we still cannot take that node. So we can just take something like this. And that's fine. And in this fashion, we got at least square root of n nodes. And here's why. The length of every simple cycle is less than equal to square root of n, right? And we know this because if there was a simple cycle with greater than equal, with at least square root of n, ceiling of square root of n, then, well, we would have solved the problem. So we're assuming that this doesn't exist, and we're trying to prove that that means there's an independent set. And if we can do that, then we can prove that one of the two conditions exists. Okay, so if we take one node from every simple cycle, then the problem is solved. However, not all nodes are part of simple cycles, right? So how do we prove that this tree-like structure, and from the tree-like structure, we're taking enough nodes? And the answer is, during a contest, you're not going to go for a super in-depth proof and everything. But the idea is you're taking about between half and 1/3 of the nodes. And here's so you know this, you're definitely not taking more than half of the nodes, right? And actually you may take a little more than half of the nodes if you have something that looks like this, then you will take more than half of the nodes. So you may take a little more than half of the nodes, but you're taking about half the nodes. And again, it's not a formal proof, and you would not want to form a proof in a contest. In something like this scenario here, taking like half the nodes. In this example up here, you're taking half the nodes. So you're taking at least half the nodes in every case. I didn't mean, sorry, instead of saying 1/3 to half, I mean you're taking about half, 2/3. And this comes from the idea that you're not going to take any fewer nodes than this, and you're not going to take any more nodes than this. Okay, so how do we use this to solve the problem? Well, let's consider what we can do to make sure to solve one of these problems. Let's look at the finding a simple set of at least square root of n vertices. I claim that if there is a graph where every single node in the graph has a degree greater than equal to d, then this means that there is a simple cycle, like simple spelled with an I, cycle spelled with a Y, of length at least d plus 1. Okay, let's consider how we can argue this. So, every single node has to have a degree greater than or equal to d. Not d nodes, every single node. So if every node has a degree of greater than or equal to d, this means that there are at least d plus 1 nodes, right? Because any one node is its own node plus it has d neighbors, total of at least d plus 1 nodes. So let's consider this graph here, where every node has a degree of greater than or equal to 2. So we're trying to find a simple cycle of length 3. Okay, what we can do is we can pick any starting node that we know is part of this, right? Any starting node that's part of this graph. So let's say I pick this node here as a starting node, and we'll give it a label 0 because, well, it's the first one that we're picking. Then we'll just go around in any path, and while there is a node that we can go to, we'll pick any random node and give it a label in increasing order. So we have 0, 1, 2, 3, 4, 5. And now there's no new node that node 5 can go to. So let's just assume that there is also an edge here. And just to make it a little more interesting. Actually, yeah, let's just give all of these. Okay, everything here has a degree 3. So now we can say that we're looking for a cycle of length at least 4. Okay, let's switch up this edge. Cool, so now 5 has exactly a degree 3. And it doesn't matter what the graph is, this is just to explain a point here. So there's no new edge 5 can go to, and it has a degree of at least d, right? In this case, 3. So this means that there are 3 edges, or 3 nodes, that have already been visited and have lower numbers in the cycle, or in the path, right? The number in the path is whatever step you reach it on. So 0, 1, 2, 3, 4, 5 is the order you walk through them on, basically. So this means that node 5, well, if node 5 were to go back to node 4, and assume that this was allowed, you're allowed to take paths in both directions, just for the sake of simplicity. So if node 5 were allowed to go back to node 4, well, then you'd have a cycle of length 2, right? 5 minus 4 is 1, plus 1 is what you add. 5 goes to 2, 5 minus 2 is 3, that means 3 here, plus the 1 extra. Let's give it a second to load. Okay. Alright, the 3 there was from 2 to 3, 3 to 4, 4 to 5. I guess it'll, there it is. Plus the 1 extra from 2 to 5 is of length 4. Right, and then 5 to 1 would be of 1 to 5 plus the extra 1. Okay, so 5 has a degree of at least 3. And actually, let's imagine 5 had a degree of exactly 3. Wait, it does have a degree of exactly 3. That was my bad. Okay, 5 has a degree of exactly 3. So this means that 5 can pick any path. Let's just say it picks the greatest one, 4, right? The length of the path, if 5 takes 4, goes to 4, is 2. Now, let's just say it's the very worst case, and the next one is 5 goes to 3. Well, it's of length 3. Then 5 goes to 2 is of length 4. So this gives us the path of length d plus 1, right? Because if 5 goes to the very highest number it's connected to, the path length is at least 2. If it goes to the second highest number, the path length is at least 3. So if the third highest, the path length is at least 4. If it goes to the dth highest, the path length is at least d plus 1. The smallest value 5 is connected to is 1. So it'll simply take this path here, and it'll get a length of 5, which solves the problem. Okay, so this solves the problem if we can convert our original graph into a graph where all the vertices have a degree greater than or equal to d. And it'll just solve it of type 2, right? Where it'll create the cycle, the simple cycle of a length of least square root of n. Now, however, this is not always the case. Sometimes we'll have an independent set. So what we'll do is, when we have our graph, we will take the node with the smallest degree, and we will put it into our independent set. We'll say, we're taking this, we're putting it into our independent set, and we'll delete all its neighbors. We will then repeat this process over and over again. Eventually, the node with the smallest degree will have a degree of at least square root of n minus 1. If this is the case, then we can find our simple cycle, because that means that all the nodes have a degree at least square root of n minus 1. If it is never the case that we get a node with degree of square root n minus 1, that means that at every step, the degree is less than square root n minus 1. If the degree is always less than square root n minus 1, and remember, when this happens, our independent set, we add one node to it, right? We add the node of the minimum degree. So our independent set size, we add 1. And then we delete some nodes. How many nodes do we delete? Well, the number of nodes we delete is the number of neighbors. The number of neighbors is, well, if the number of neighbors is less than square root of n minus 1, this is equivalent to saying the number of neighbors is less than or equal to square root of n minus 2. So the maximum number of neighbors we're deleting is square root of n minus 2. This means that the total amount of nodes removed, because again, the node that we're adding to the independent self, we're also removing it. The total amount of nodes we're removing is square root of n minus 1. How many times can we do this? Well, it is at least square root of n. Because note that if the total number we're removing was simply the ceiling of square root of n, the times we could do this would be the floor of square root of n, right? So since this is the ceiling of square root of n minus 1, we can do this at least the ceiling of square root of n times. Okay, so if we're able to do this, the ceiling of square root of n times, then we've solved the problem in type 1, where we found an independent set of exactly square root of n vertices. If not, then this means that we have all the nodes have a degree of at least ceiling of square root of n minus 1, and so we can find a simple cycle of at least ceiling of square root of n nodes. Let's consider the code for this. So the first thing we do is we have n m, and we want to store the ceiling of square root of n, just so that we know what that is. So we read in nm, we get the ceiling. Now we have to make the graph. So the graph is going to be a set of integers for every node, which stores all the neighbors. And this is so that whenever we're removing nodes, when we're checking for the independent set, we can easily remove a node by removing all of its neighbors, because it's a set and we can delete in log n. Okay, so for every edge, we read in the two edges and we change it to zero-based indexing. For node A, we add B as a neighbor. For node B, we add A as a neighbor. Okay, we now need to be able to store all the edges by their degree, or by all the nodes by their degree, in some way that we can keep getting the smallest degree. For that, we're going to have a set of pair intent, which is the nodes. So the first value stores a degree, the second value stores the node index. So like a degree 5 for node 2, degree 6 for node 3, and so on and so forth. And this will be an iterator that just helps us iterate through. And vector int answer is the list of nodes that we will output in our answer. So first we're going to assume that we can find an independent set. So into our node set, we're going to insert a pair of, for every node, its degree and the node. Okay, we're going to take the first node, and we're going to keep repeating this while there are more nodes left, while the degree of the smallest node is less than square root minus 1, and note that this is equivalent to saying less than equal to square root minus 2, and while the answer size is less than square root. Because if you recall, they say that we need to output exactly square root of n vertices, not more. Which is fine. An independent set, you can remove a node from an independent set and it still is an independent set. So the node number is the that second, and recall that's because the first one is a degree and the second one is the node. So we take the node index, we add it to our answer because we're assuming that we can do an independent set. Okay, we then erase it from the list of potential, from the list of nodes with sorted in order of degree. And we erase it here because we're going to do some adding and deleting stuff here, and it's just cleanest to erase it here. Now we're adding the node to our independent set, so we have to erase all its neighbors. So we loop through all its neighbors. We're erasing it from our set of all possible nodes because we don't want to, that's this thing here, this thing here, and that's because we don't want to add the new node to our independent set, right? Sorry, not the new node, the neighbor node. We're deleting it, so we erase it. Now, we also delete all of the neighbors' neighbors. They're just gone. We don't want any more of these. Okay. For that one neighbor node, though, we deleted it from our set of nodes, but we also have to delete all its edges. When we delete all of its edges here, but note that all of its neighbors also store it as an edge. So for each of its neighbors, if the neighbor is not equal to the node that we're starting with, right? That's the node that we've just taken out. Then for that node, we erase it. We also want to update the degree size of node j. So we erase node j from our set of nodes, and we insert it again with the correct degree size, which should just be -1 for this. Okay, now for our node, we have deleted all its neighbors, right? Now we need to delete the node itself. We don't want to use it again. So we've already erased it from our set of nodes, which is going to erase all of its neighbors too. We've erased all its neighbors, we're erasing all of these too. Okay. So now the node is removed, is added to our independent set, and all of the node's neighbors are removed. If there still are nodes left, we update it to the first item in the set, so we can repeat this process. And note that we set it to the first item in the set here too. Now that we've exited this loop, there's two cases. The first case is that the number of nodes in our independent set equals square root of n. This means we found our answer. So we output 1, and we output our answer, a new line, and return 0. So we end the program here. If not, then it is the case that all of the nodes that are remaining have a degree greater than equal to square root of n minus 1. And all of the nodes that are deleted have 0 neighbors. We made sure here to clear all its neighbors, and that is so that we know which nodes are remaining after. Okay, so we clear our answer array, and ignore num for a second. We clear our answer array, and this basically means that we're not using the independent set. So all the nodes that we said were in the independent set, we're kicking them out. Because right now we're looking for a cycle of like square root of n. Now, num will store, you recall from here, these red values here, 0, 1, 2, 3, 4, 5. Basically doing the same thing. We're picking a random value as our starting point. We're going to go through the whole graph, giving every node a number, and we're going to keep increasing it until we find a node which has no possible neighbors, and then we'll take its neighbor, or say no possible unvisited neighbors, and then we'll take the neighbor with the smallest value and make the cycle. And that cycle is guaranteed to be of length d plus 1, at least d plus 1 as we've proven. Okay, so we're going to originally set everything in num to -1, and num is an interarray. Then we're going to go through all the nodes. If adjacency size is not equal to 0, this means if it is not deleted, right? So nodes that were deleted were nodes that were either in our independent set or their neighbors. The nodes that are remaining are the ones with size with degree at least square root of n minus 1. So we're ignoring deleted ones. If it's not deleted, we set num I equals to 0. So that basically sets it as the first one on the path. And then we start DFSing from that node I. And then we break, because we don't want to repeat this for a future one. And after this break is unnecessary, because DFS ends the program. Ends the program once we found the whole entire cycle. So this break is technically unnecessary. Okay, let's look at our DFS. So what the DFS is going to do is going to add all these 0, 1, 2, 3, 4, 5 to the answer vector in order that we see them, but it's not going to print out the whole entire answer vector. So when 5 figures out that its neighbor has a value of 1, it'll print from 1 to 5. Or if this edge did not exist and it was of neighbor 2, it'll print 2 to 5. So yeah, so the first thing it does is it adds the current node to our answer vector. And again, we're doing +1 because the program uses 0-based indexing, we should output 1-based. And that's the same reason we did add +1 here. We add nodes to answer. Okay, back to this. So we first need to see what count does is it sees, do we have any neighbors that are not yet visited? And we know it's not visited if the num is -1. So if it's the case that we have no visitors, well then we want to find the one with the smallest num. And all our neighbors will have num smaller than ours, right? So we're like 5, we're the biggest one. So this is just a thing that just is a filler. But basically what we'll do is we'll put the num, like the number of it, and the node index here. And so the number goes here, the node index goes here. We'll just keep taking the min. And so it'll take the min of the number first, and it'll help us store the index. Okay, so we loop through every item in the adjacency that's like next to the current node, all our neighbors. If the num is -1, then count ++, and this means that there is some number of neighbors. The number of it is our number +1, so 0 goes to 1, then 2, then 3, then 4, then 5, and then we DFS. Now note that we will not end up DFSing twice from the same for loop, just the way the program works, but we don't have to code that in. Okay, if the num_i is not -1, which means we've already seen it before, then we update the smallest value. And we could actually update the smallest value even if we had seen it, even if num_i is -1, just because while this would set to -1 for this value, we're never going to use small if there is a neighbor we could go to, right? So 5 only uses it because it goes to 1, 2, and 4, because there are no neighbors where the num_i is -1, but that's fine. Okay, so now if it's the case that count equals 0, then small will give us the neighbor with the smallest num value, which will give us the biggest cycle. So the cycle length is 5 minus, this would be 1 in this case, plus 1. And that's just for the red graph on the left-hand side. So 5, so numat minus small dot first, that'll give us the length of the existing cycle. And just to reiterate, that's this part here. And it's this part here. And the plus 1 gives us this extra edge that we have to add in from 1 to 5. So that's the number of edges in the cycle. And then we loop through all of them from small dot first. I is less than numat plus 1 is less, the same thing as saying I is less than equal to numat. I don't know why I did it this way, but it's the same thing. And then we say, and then we just print them out. So we'll start from 1 and we'll keep printing the indexes of, we'll print the index of this node, then the index of this node, index of this, index of this, index of this. So remember, 1, 2, 3, 4, 5 are not the indexes. That's the num value. So we'll print all the indexes and then we'll end the program. And that's the solution for this problem.